Welcome to section 11.2. We're going to do more area stuff. The last lesson we did the area of a parallelogram and the area of a triangle. Well, this first thing right here, trapezoid, it has some similarities to a triangle. Let's put a trapezoid down right here. And, oops, let me grab this thing. There we go. I just want to kind of show you the similarity we have between trapezoid and a triangle. It's going to help you remember the formula for the area of this. If you remember that the area of a triangle, okay, the area of a triangle is, well, let's write it like this. The base times the height divided by 2. So we multiply the base and the height, we divide it by 2. And if you remember from the last lesson, the base and the height have to be perpendicular to each other. All right, so it's very important that the base and the height are perpendicular, divide it by 2, and you got the area of a triangle. Well, the area of a trapezoid is pretty close to that. Let me just kind of show you why, I guess. Not exactly why, but just show you some similarities. Oops, almost dropped my book. All right, here we go. Now I'm ready to go. What I'm going to do is take this side and just kind of extend it out like this, and take this side and extend it out like that, and we'll take this one so it meets up with that one. There we go. So what we did is we took this trapezoid right here and it just extended both of the sides, and if you take a look at that, it looks like a triangle. And again, I'm not getting real specific with this. I'm not getting real detailed, but I just want you to understand that the area of a trapezoid, just this part right here, is pretty close to the same thing as the area of a triangle. If you look at the area of a triangle, we have base times the height. So if I consider this the base, where is the height to this thing? Let's do a different color. And where would the height of the triangle be? It would be from the top, and it would be perpendicular to the base. So that distance right there would be your height. So if I call the bottom the base and this blue one right here the height, and you multiply them together, divide by 2, and then you've got the area of that whole entire triangle. Well, of course, this isn't a triangle, is it? Let's get rid of some of that. There we go. Let's go back to our regular trapezoid, and you're probably wondering, why did I go through that triangle stuff? Well, hopefully you'll see. Let's just make this a little bigger so we can see it a little better. And there we go. Change my color. Now I'm ready. What we have here is a trapezoid, and remember, both of these are parallel to each other. I'm not even going to draw that in there, but they are both parallel to each other, and they have two bases. If you remember before when we talked about trapezoids, you have we'll call this B1 for base 1, and we have B2 for base 2. So we actually have two bases. We don't just have one. Area of a triangle, we just had one base. It was the base times the height divided by 2. But the area of a trapezoid, okay, I had to pause there for a second. Somebody came into the room, and now I got to remember what I was saying. I got two bases right here. So the area of a trapezoid is really close to the area of a triangle. So let me just write down what the area of the trapezoid. Remember, the triangle is the base times the height divided by 2. Well, this trapezoid has two bases, so this is what we're going to do with the two bases. We're going to take the two bases and combine them, add them together. So I'm going to take the first base and the second base, add them together, doesn't matter what order you add them, multiply by the height, and divide it by 2. See how that's really close to the area of a triangle. Base times height divided by 2, except a trapezoid has two bases. Sometimes they'll write it like this. This probably looks a little bit neater. It's all on one line. So a lot of times books will write it like this. 1/2 the base, in this case I have two of them, so I add the two together. So 1/2 the base times the height. As you see, it looks really, really close to a triangle. Now look, trapezoid starts with a T, triangle starts with a T. So there's definitely a relationship just between the two words, and there's also a relationship between the two formulas. It's 1/2 the base times the height. In this case, though, you add the two bases together. Now the height, remember, is perpendicular. So where is the height on this thing? Well, the height would be from here, perpendicular to both bases. Okay, it's got to be perpendicular to both bases. And so it's perpendicular right here. It's a right angle here, right angle there. So that would be your height. Of course, you'd add up the two bases, multiply by this height. Now, if you take a look at this height could be anywhere along here, right? That could be the height. or that could be the height, or you could go all the way to that point right there. A lot of times they'll do that. They'll go to where this top point is and go perpendicular to the other one. But that's a right angle, that's a right angle, that's the height. It's still the same. All right, that height doesn't change all the way here. Why doesn't it change? Because it's a trapezoid and these two lines are parallel. All right, so that's the area of a trapezoid. Let's move on and take a look at a rhombus. Remember, this is plural for rhombus, and a kite. Okay, here I have a rhombus and here I have a kite, and what I should do here, this has some diagonals drawn in it. Remember diagonals? And that's what we're going to do here. We're going to draw some diagonals on this one. So here would be one diagonal and here would be another diagonal. All right, and those diagonals are important for the formula that we're going to use here for a rhombus and a kite. And the reason I put both of them together is because they have the same exact formula, which is kind of nice. So I'll put A equals, and here it is. We still use that 1/2, just like we did on a triangle and just like we did on a trapezoid. We're still going to do the 1/2. So we're going to go 1/2, and then what we do is we talk about the diagonals. There are two diagonals, and they're not necessarily equal to each other here. Unless it was a rectangle or a square, they would be equal to each other on a rhombus. Okay, but on a regular rhombus that doesn't have any right angles, these would not be equal to each other. So what we do is we take the two diagonals and we just multiply them together. So I'll call one diagonal D1, I'll call the other diagonal D2, and that's it. Pretty simple. You just have to memorize it, right, and understand what it means. Now, if let's kind of mark it, we'll call like this one right here. That's probably not a good place to put it. We'll do like this. Okay, this one right here would be D1, and then we'll do like this. This one right here would be D2. So the length, if you wanted to, you could put ABCD, and you could say that AC times BD, multiply the two diagonals together, take half of it, don't forget to take half of it, that's going to be the area of that rhombus. Same exact thing with a kite. You have two diagonals of a kite. So you've got this one right here. We won't mark it up. I think you understand what I'm talking about. So from here to here would be one diagonal. Here to here would be another diagonal. How do we find the area, right? All the stuff inside of here. How do we figure that out? Multiply the two diagonals together, take half of it, then you got the area of this whole entire thing. So that's how you find the area of a rhombus and a kite. All right, let's do just a couple examples and we'll be finished. It's that easy. So let's do an example. Let's actually go back to the trapezoid, and we're going to show you the kind of stuff they're going to give you to do on the problems here. Okay, here's a problem that you're going to have to combine a couple things together. So let's take a look. This is actually, it's example in the book, and it looks like they say it's a standardized test. So this is something that very well could be on the SAT, or something that looks like it's on the SAT from what the book is saying. So we have to find the area of this whole entire thing. I'll just put find area. And you're like, wait a minute. This, is it a trapezoid? Is it what? What is it? No, is it a trapezoid? We've got this parallel side to this parallel side. You got this and you got this. Let me think here a sec. Yep, this thing's a trapezoid. So how do you find the area of a trapezoid? Well, it's 1/2 the sum of the bases. So I add the bases together multiplied by the height. So let's see what we have here. What would the bases be? Well, the bases would be the two parallel ones, and so this isn't on its side like we first showed. We kind of tipped it up a little bit, but this would be a base and this would be a base right here. The problem is I don't know this base. I'm gonna have to call that x. So it would be really nice because the height would be 4, because if you look at it, that would be perpendicular, and they tell you in the problem that that's perpendicular, and that's perpendicular right there. So they do tell you that they're right angles. The issue is solving for x, so we have to solve for x. So how in the world are we going to do that? Well, good question. Let's see if we can figure that out. Here's one thing that we might want to do is let's take this over here. So this is the same length as this bottom right here. So if this is 4, this would be 4. Now, why in the world did we do that? Well, that kind of helps us a little bit because at least I have a triangle here and I've got a little rectangle. Let's see what we can do. But what is the 10? The 10 is from here all the way to here. All right. So again, this is what we're trying to solve for. And now, of course, if this is x, that's what we're trying to solve for. This part from here to here would also be x as well. All right. So that might help us a little bit. What's the problem, though? How can we solve for this? Because I know this is 10. If I knew this part right here, watch this. If I knew this part right here, then I could take it away from 10. And then if I took it away from 10, that's what this x would be. And then I'd basically be done, right? Because that's our key. I know what the h is, which is the 4. I know one of the bases, right, which is this whole thing 10. It's this part right here I want to find. That's one of my other bases called b2. So that's what I'm trying to find, is that x. Once I do that, I just plug and chug. It's no big deal after that. So let's see what we can do here. Let's go a little more color here. Let's find from here to here. Let's see if we can find that. Any ideas? Well, this is a right angle. They're parallel to each other. That's a right angle. That's a right angle. And look what I have. I've got a right triangle. I know the hypotenuse. I know one of the legs, and we'll call this, let's not call it x. Let's call it something else. Let's call it, let's just call it a. All right, so I could actually find a by doing Pythagorean theorem. So let's go ahead and do that. It's going to be a squared plus 4 squared equals 8.5 squared. To save you the time, let me see, they do it in the book. Right, to save you the time, I'm just going to solve for a, and that would be 7.5. I think it's approximately 7.5. I don't think it comes out exactly. But anyway, you put this in a calculator. You can do the work. Just saves us a little bit of time. And then a is 7.5. So this right here is 7.5. So if this is 7.5, the whole thing is 10. How do we find this part right here? We just subtract. So 10 minus 7.5 would be 2.5. So this would be right here 2.5. So if this is 2.5, so is this. And that's what we were trying to find. So now we can find the area. So if we find the area, it's 1/2 of one of the bases, 10 was the base that we originally knew, times the other base, that's what we had to do that work for, and that's 2.5. And you just work that thing out, and you work that thing out, and it comes out to 25. All right, so that would be 25. And it's square whatever. I think it's in inches, so we'll say it's inches. Inches squared. That's how you find the area of that whole entire thing. All right, this example is way more straightforward than the other one was. It just says find the area of this kite, and look, they put it up here. They didn't really mark it. It's kind of hard to mark it here because you know, got that intersection right there. Where do you put the 8? It's kind of hard to tell. So what they did right here was they went from here, which is this point, straight across to this point right there is 8. So this diagonal is 8, and this diagonal from top to bottom, that's 15. So how do you find the area of a kite? It's pretty simple. It's 1/2 the product of the diagonals, which means d1 times d2. And look, this is really straightforward. They tell you both of the things. They tell you the two diagonals. All you do is just plug and chug. So it's 1/2 times 8 times 15. And let's see, half of 8 is 4. 4 times 15 is 60. So the area is 60. And it's whatever it's in. Let's say it's in centimeters. I don't know what it's in, but we'll say it's centimeters squared. So area is always squared. And that's the area of that kite. Let's do another one. Let's do a rhombus, and we'll be finished. Okay, here's the last example. We're going pretty quick today. So again, it's very straightforward. It just asks you to find the area of this rhombus. Now they tell you it's a rhombus. What do you know about a rhombus? Well, you know that a rhombus, the diagonals are perpendicular. That's one thing you know, but you don't really need to know that for finding the area. Another thing you need to know is that the diagonals bisect each other, okay? They bisect each other because it's a parallelogram. So this time they only give you this little bit right here, which is 6. Well, that tells you that this is 6 because you know it's a rhombus, which is a parallelogram, which means that both of these are exactly the same. So that whole thing is 12. That's one of my diagonals. Same thing with over here. They bisect each other. So if this is 7, this is 7. So my two diagonals are 12 and 14. So to find the area, remember it's 1/2, don't forget the 1/2, times one diagonal, which is 12, times another diagonal, which is 14, and then we can work this thing out. You don't need a calculator for this. Do this. Watch. Take half of 14, which is 7, right? So the 1/2 and the 14 comes 7. And then it's just 7 times 12. You can do that in your head, and that's 84. It's area, so it's squared. Let's say it's feet this time. I'm just making it up. So let's say it's feet, so it's feet squared. So the area of this rhombus would be 84 feet squared. Let me just take a quick peek, see if we didn't miss anything. Yeah, I think that's pretty good. Oh, they have another one in here. Let's do one more example. Sorry, got y'all excited for almost being done, but we got one more example to do. Okay, I promise this is the last one. So they tell you something a little bit different. They tell you the area. They actually tell you what the area is. They don't ask for the area, but they don't even tell you the diagonals or the lengths of the sides or anything. They just say that they say that the longer, or one of the diagonals is twice as big as the other one. All right, so one is twice as big as the other. So just call one, I don't know, call it X. Just had another interrupter in my room. Same person. So anyway, let's try this again. This is one of the sides is X. It says the other side is twice as big, or not side, but one of the diagonals is twice as big as the other diagonal. So if this one is, we'll call this one X. Remember, the diagonal is actually from here to here. We just put it out here just to kind of show the length of it. So this is X, and this right here is going to be twice as big as this one. So I'll call that 2X. It's ugly too. Let's try that again. All right, so this would be 2X. So that'd be a nice way to do it. They don't actually draw the picture for you on this problem. It's just a word problem. They say one of the diagonals is twice as big as the other. So I'll call the shorter one X. I'll call the other one 2X because it's twice as big. And they tell you the area. So now it's just a matter of putting it into your formula. Let's write the formula down again so we remember it. So it's 1/2. Remember what this one was with the diagonals. It's D1 times D2. So now we can put some stuff in here and actually solve. So this is going to be 169 equals 1/2 times one of the diagonals, which is X, and the other diagonal, which is 2X. It doesn't matter which one you call what. And now they just want you to solve for X. Yep. Let me see. What is the length of the diagonals, actually? So we got to find X, which would be one diagonal. You just double it, and you got the other one. That's not that big of a deal. So let's just solve for X. Let's see how we can do this. Well, 1/2 times 2. I can just do that right away, couldn't I? Half of 2 is 1. So what is this? This is just X squared. So this is X squared equals 169. Now, 169, if I take the square root of both sides, comes out perfectly to be 13. So X is equal to 13. So that's what that diagonal is. Now this is just twice as big as 13, so 2 times 13, which would just be 26, and there it is. Now this is not squared. The area was already squared, so this is just 13 millimeters long, and this is 26 millimeters long. So you don't square the lengths, you only square the area. So it's a little bit different. Not that big of a deal. I hope you follow it along. Okay, look at that. Under 20 minutes. You guys said in class today you like the ones under 20. So we did it again. All right. Enjoy this lesson. We'll see you next time.